Right. Good afternoon again.
Good
So, because we have to cover quite a few topics, I think we should start.
Yes, sir. You can start,
Um,
sir. In the meanwhile, the participants will join. You can start, sir.
sure. So the plan is in this. It's not uh, exclusive, but it's still fairly long list. Um, I will cover. I will not go through Fabry-Perot cavity antennas today because we are going to do it more comprehensively later. And also leaky wave antennas, I have uh, slides that I can do when we return, when I return Wednesday. So let me try to cover the other types of antennas. Um, Wire antennas, we already mentioned, dipoles, loops, microstrip antennas is very common, probably everybody knows, but I will show you something that is similar, an extension of microstrip later. Printed monopole antennas. So I already mentioned the dipoles and monopoles. Um, Dipoles and monopoles, they are kind of wire type antennas, but in fact you can print some type of monopoles and dipoles and make them easily used in printed PCB, printed circuit board method. I'll show you one example. Stop sharing this and share different set of slides. Um, Printed monopole. So how do they look like? Um, this is a typical printed monopole. Um, See, there's a ground plane, but this is a FR4 laminate, and you can see these tracks printed on one side, and the other side has a ground plane. So ground plane is on one side of the dielectric, the radiating elements and the transmission lines, microstrip line here, feeding the antenna on the other side. So everything printed can be manufactured very cheaply using printed circuit board method. These are the radiating parts. You can see there's no ground plane underneath the radiating element. Ground plane is only under the feed. So it sort of behaves like a monopole. And this work we published long time ago, 2005, at IEEE Antennas and Propagation Symposium. You can see different shapes. Uh, this one was one of the very early quad band printed antennas for Wi-Fi. If you look at the title, it's a quad band Wi-Fi antenna for wireless local area networks. It's called quad band. It's actually a dual band antenna. It covers the 2.4 gigahertz IEEE. It's either 11B and G band, uh, and then 4.9 gigahertz and 5.2, 5.8 bands, uh, higher frequency bands. This at that time. Still, these are the bands used for Wi-Fi, but now we have more standards. So that gives you an idea how it looks like. We fabricated them, we tested them, we measured the return loss or input reflection coefficient. So this is S11 magnitude. In other words, the reflection coefficient magnitude. You can see minus 10 dB bandwidth. So this is the return loss is opposite of that. So it's 10 dB return loss here and here. This is the lower band, this is the upper radiating band, higher band and lower band, and radiation patterns, etc. The prototypes, you can have two of them in one PC MCIA card. Those are the cards that used to be available for laptops, etc. Those days, because if you do, those days laptops did not come with Wi-Fi. You had to attach this PC MCIA card to have to enable Wi-Fi connection. Okay, so now the second type are ultra-wideband printed antennas. So that is even broader than multi-band quad band. You can get even wider bandwidth using this kind of antennas.
So there is no slide, I think.
Yeah, there's no. I had to change to another. Okay. See that done. Okay. So this was one of my PhD students from India. He did this, I think, when he was a PhD student, then he was a postdoc. Now he's in Australian government, very high position in the public service. So these are all ultra-wideband, so-called ultra-wideband antennas. Some of them have bandwidth from 3.1 to 10.6 gigahertz, extremely wide bandwidth for pulse operation. That's what people are proposing at those days. I will not go through the context part, but these are kind of antennas people design. That is a very wide slot in the ground plane. So this is metal, this is a slot on the ground plane, it's all printed, right? And then you feed it from the other side, like a microstrip line. So the slot radiates. Slots are very much like microstrips. Microstrip is a patch on the ground plane. This one is a slot in the patch is, so micro patch is a patch on the ground plane with substrate in between. These slots are hole in the ground plane, but then you have to feed it to the transmission line. But this is not our work, this is previous work. So this is like a bow tie slot. These are all metal ground plane. This is a slot radiating element. And the feed here is a coplanar waveguide. It's not a microstrip, it's a coplanar waveguide. So you can more or less do everything on one side of the substrate in the printed circuit board. Then our antenna is this. This is again a ground plane metal on one side of the substrate. Then they cut these slots, etch out these slots. So that's a radiating element. And there's a coplanar waveguide transmission line. That doesn't give good matching, but then we added these impedance transformers, stepped transformers to get good matching. So there are different designs with different matching on Smith chart, impedance, reactance, and resistance. As I said before, the resistance changes with frequency, the reactance changes with frequency. You can see both on the Smith chart. And these are the measured input reflection coefficient magnitude, which is less than 10 dB, a very broad range of frequencies. We got 3.1 gigahertz to 10.8. That is what we need 3.1 to 10.8, but we actually got even wider match bandwidth from this antenna. It's not too difficult to get that kind of bandwidth from printed monopole antennas. And in fact, there are other ultra-wideband antennas like monopole type. They have even wider bandwidth. But the problem is at different frequencies, they have different radiation patterns. These are the radiation pattern plots. At different frequencies, they change with frequency. So that is an issue. These were designed to apply not to continuous waveform, as a pulse waveform. The radio initial concept of ultra-wideband was there's a pulse. It's a pulse system. You apply a pulse and then receive the pulse. That's why we did the pulse analysis, pulse distortion, etc. We published several papers in IEEE transactions on ultra-wideband. You can find a lot of those papers. I just want to give you a very quick overview of ultra-wideband printed antennas. Then there are 3D antennas like spirals and helix. I will just give me a second. Did I miss? So that you can get an idea about the gain you can get from this kind of antennas. This is 3.5 dBi. I should be here, but it's not flat. It has one plus or minus 1 dB variation. We tested the pulse performance and pulse distortion, the transmitted pulse and received pulse. Always there's pulse distortion, but this found to be acceptable. Yeah, that's the measured gain versus frequency in dBi. And as I said before, this is the biggest problem, change of radiation pattern with frequency. At low frequencies, this kind of antennas behave more like monopoles, but at higher frequencies, they behave differently. It has more like higher order mode problems. So the pattern is not standard omnidirectional pattern you expect from a monopole. But bandwidth, match bandwidth is good, but the gain bandwidth and the radiation pattern consistency is not very good in all antennas of this type, our one and the others. Some of them are not slot, I think. This is also a slot, 2 slots in a ground plane. So this area is metal. This is no metal removed, etched out. This is a little bit more complicated one. This is just a very simple slot, big slot in a ground plane, fed by a microstrip line on the other side. I showed you this already. Okay, I will cross that out. Now, dielectric antennas. Dielectric resonator antennas. So the dielectric resonator antennas quite common. A lot of research is done even recently in India. We had done a lot of research in this area quite a while ago. I have written invited book chapters, etc. So go to book chapter. I think I have the book chapter open somewhere here, maybe a PDF. Let me try to find that. Yeah, okay, here it is. Now share. This book may be available in your library. This is probably the most cited book on dielectric resonator antennas. Edited by Professor Luke and Professor Leong. Both of them are from City University in Hong Kong. So they invited various authors who are doing research in this area to write chapters. So I wrote an invited chapter on low profile antennas, but there are a lot of other chapters about the dielectric and resonator antenna concept. From overview, so this is an alternative to microstrip patch antennas. Instead of a microstrip patch, which is basically a printed device made up using printed circuit technology. Dielectric resonator antennas normally made out of dielectric blocks, so they are not printed. That is a disadvantage, but it gives you more flexibility to make them in different ways, especially that now you can 3D print the dielectric and metal to any shape. There's a lot of interest in these antennas for 3D printed in the 3D printing domain. So otherwise, it's a block of dielectric at the resonant mode. You excite the resonant mode of the dielectric block using a feed, and this dielectric block, it could be spherical, so half a spherical, rectangular, circular, cylindrical, and if you excite it properly, the right mode, it radiates very efficiently. Very good radiation efficiency, very low loss, as long as you use low loss material. So you can see the red cylinder, very different shapes, hemispherical, and so you may have this, probably you have this book in your library. You can make arrays of these. The Communication Research Center in Canada, in Ottawa, they made these kind of arrays. I have seen them in Canada. Actually, these Aldo Petosa, Pisak, they were in Communication Research Center. So rectangular antennas. So that's a rectangular block, rectangular electric resonator. Let me fast track and try to find my chapter. Hemispherical. Because the challenge was to design very low profile. Those days, almost all dielectric resonator antennas were fairly tall. So I designed two antennas that are low profile. I published both of them in one in IEEE transactions and one in IEEE, so electronic letters, I think. So that was the topic of my chapter. I think it's low profile. Yeah, here it is. Low profile dielectric resonator antennas. So the idea was to minimize the height, make it more like a microstrip. It's still taller than patch, but and then this is the feed substrate. This is the feed transmission line. Here's a slot in the. This is the ground plane, and there's a slot in the ground plane that couples the field coming from this into the dielectric resonator. And in fact, we made the circular polarized one as well. Linearly polarized, these are circular polarized radiation patterns. This is the linear polarized one, typical configuration. Circular polarized one looks like this. The feed slot is that, and we rotated the dielectric resonator at an angle. So the feed excites two orthogonal modes in orthogonal directions, plus 45, minus 45. And they resonate at different frequencies. So when they resonate, there's a 90-degree phase shift between the two. So that gives the necessary condition to generate circular polarization. That means 90-degree difference in the mode vector and also 90-degree phase shift. So you can, if you can't find this book, actually you can find a couple of my papers in that. Okay, let's move on. Cross them one by one. So you have what is the next in the list? I will check it. Hybrid antennas, go to paper. Now, hybrid antennas are not very popular. We published this paper. I published with Dr. Trevor Bird, who was later was the editor-in-chief of IEEE Transactions, but this was before that. The hybrid resonator antenna. So this is in IEEE Explore, so you can download this paper from your university. Do you have Explore in the university? From your, so this is publicly available through Explore, not in open access. So why it is hybrid? It is a combination of a microstrip patch and a dielectric resonator. Can you see this? Maybe I should zoom it up, right? So you can see it has similar features. A slab, the feed substrate, microstrip feed, the ground plane, and the slot, just like a normal dielectric resonator antenna. But then we squeezed a microstrip patch between the two. It's just like the stack patch, microstrip patches. Stack patch antennas is like one microstrip patch and another patch above it, two patches. Normally they are designed to resonate at two frequencies. Some are close to each other. So because of the double resonance, you get wide bandwidth. That's exactly what you're getting here. The dielectric resonator resonates at one frequency, the patch resonates and radiates at another frequency. So as a result, you can get matching, good matching. So this is S11 magnitude. This is basically the raw I mentioned in the first lecture, input reflection coefficient magnitude. We usually want it below -10. This below -10 means good matching. That means return loss greater than 10 dB. So you can see that the patch alone, if you have the patch antenna only, this is how it works. So it's not very well matched. It's matched only here. The dielectric resonator antenna only is the dotted line. So it radiates at a higher frequency. When we have the dielectric resonator on patch, DROP, drop, dielectric resonator on patch, this hybrid antenna, this is the input matching, so it's less than -10. Return loss is less than sorry, not return loss, sorry. Reflection coefficient magnitude is less than -10 over very wide bandwidth. And their patterns are similar as well. So that is an example of a hybrid antenna. Okay, just checking the list. So Fabry-Perot resonant cavity antennas that we will discuss later. If you want to just have a glance at the list again. So we looked at wire, we did not look at microstrip, but you saw microstrip in the hybrid printed monopole. We look at that. UW, we look at that. We haven't really discussed 3D antennas except this helix I mentioned earlier, helical antennas or helix. But you can make other spirals, you can 3D print those. These days, there are a lot of possibilities. Dielectric resonator antennas, dielectric antennas, and so that's what we just looked at. And hybrid antennas, dielectric resonator on top. We look at the paper. Then the Fabry-Perot and resonant cavity antennas, we will go through this possibly Thursday. And leaky wave antennas possibly Wednesday. So that leaves some time for us to go through implantable antennas and some printed inverted F and flexible antennas and active antennas. The other antennas, I don't have slides, lens antennas, because they're quite, actually when we get to the Fabry-Perot, I will mention some few things about lenses. Aperture antennas like horns. I think I have a short horn paper that I can show you. And reflector antennas are like dishes, parabolic dish antennas that are very common. It's basically a ray optics type dish. And antenna arrays, you saw one array out of dielectric resonator antennas, and you will see few arrays later. Okay, so going back, we should look at the implantable antennas, right? MTT transmission, transaction paper, and Y-bend slides. So the MTT, we published one paper in the IEEE transactions on microtheory and techniques, MTT. Let me find that. Okay, I found it. I'll share it. So, I guess you can read, right? You can find the title. So this is another one available in IEEE Explore. No other sites and transactions. There's a long story to this. I think I have some slides too. That may be less boring than this paper. First, I will show you what is in the paper. So this is a biotelemetry system. Okay. Biotelemetry system means you transmit biological data from a biological body. In this case, the intention was to implant this inside rats. When medical Paul Pilowsky is a professor in medicine, so we have done this project jointly with experts in medicine and Australian School of Advanced Medicine. David Bull has a company. He's an engineer. He joined as an industry partner, and the other two are university researchers, including myself. Let me check whether the slides. Yeah, I think I'll share the slides because that has a nice story. If you want the details, take a note of this paper. Right, take a note of this, and you can download and read all the details. But a good summary is in these slides, which I think I presented in some conference. So I will switch sharing to the slides. So antennas for implantable biotelemetry and wireless body area network systems. I was director of the Environment Research Center in Macquarie University before I moved to UTS. So this work was a multidisciplinary work and done with, as I said, industry, professor in medicine, and some in CSIR, some collaborated, including Professor Anand Verma from University of Delhi South Campus, and so on. So what is the problem? And this is actually a real RFID-based biometric data collection system that was, I think, developed by US Army for soldiers, that was used in actual war situations to monitor the health, especially the temperature of soldiers when they are in the battlefield. So it's a real device. It was integrated, I heard it was integrated to, it was used by Australian soldiers as well. It was integrated to a jacket. So we were given this device, but our project is not military or defense. We wanted to use it for medical application, to implant this inside rats. Inside rats, when the medical experts do experiments with the rats, they need to know a lot of things inside the rat, not just the temperature in different organs, pH, nerve activity, and so on. So the sensors, this has the capability to attach a daughter board with, and that are connected to the sensors, so you can collect all that data and wirelessly transmit that data to a device like this. This is outside. This is the RFID reader. The only problem is when you put this inside a rat, the antenna is detuned. It totally detuned and doesn't work, because this antenna is designed to work in free space or in air, not under the skin of a rat. So our job was to design a new antenna that is this size or smaller and pin compatible. We are not allowed to change any other things because we don't know what are these. Pin compatible, so that when you when you integrate it to the system and put it under rat or under rat skin, it works. So this is the original, and this is the one we designed actually and prototype. And it has some, we had to do some fiddling, and this is our antenna. It's actually smaller than this original one, and it worked. We integrated it, we put it with biocompatible material. So that's the whole PhD thesis actually. This is the paper I mentioned, and we tested. We did not implant it inside the rats, but we got fresh rat skin from medical school and put it over, covered the antenna and the whole RFID tag by the rat skin, and ran the system, and it worked. And it worked up to about almost a meter, 0.8 meter, I think. We could transmit, and we can read the temperature from the sensor using this system. And that is sort of the range you need in a rat experiment, because you can place this outside the rat cage. So that kind of 0.8 meter is enough as the RFID wireless range. You can't put these things inside the rat cage because rats eat everything. So you can't put anything outside rats either, because they eat it, or the other rats would eat it. So it has to be implanted. And now the other type of antennas we looked at in this center are wearable antennas. These are not implantable, these are on the body for various purposes like healthcare and defense for soldiers, firefighting and rescue. Like the one I mentioned before, integrated to jackets, and sports, when you are doing sports, to monitor your vital signs, like a Fitbit type devices. So we work quite a lot in flexible antennas, printed antennas. First, not flexible like this, to get the right performance with simple models of fat and muscle, and later some very cute flexible antennas. We used various models, the hand models, body models. Still, these are not flexible. And this one we tested in the USA, partners in Professor John Wallach's lab on his body models. And we wrote joint papers with John Wallachis, etc. So these are also not very flexible, but they are more like a printed monopole type antennas, strips. And then we got flexible, really flexible ones. These are some examples of flexible antennas. This is on a flexible PDMS substrate. PDMS, polydimet. I can't pronounce that. Just call it PDMS. And the antenna is actually embroidered using the embroidery machine that can use conductive fibers like a copper fiber. It's very similar to normal embroidery machines made by the same companies, I think, brother, but it's a special machine that can use conducting fibers. So when you do an embroidery like this, you can automate it, you can design it and run the machine. It makes this piece. So you can recognize that this is a kind of a printed monopole antenna, right? This is the feed, coaxial feed. This is the radiating part on one side. Normally it would have metal all over conducting, but this one has a slot that is for a different purpose. And then on the other side of the PDMS substrate, there's a ground plane. So if you flip it over, it looks like this. This is the ground plane, and this is the patch. You can see through the PDMS. And it has very wide bandwidth. You can see the match bandwidth, massive bandwidth. And that is quite flexible. So we done both flexible and non. This is not very flexible. This is on a solid antennas and use some carbon nanofibers for other purposes. So that is that presentation. I think that covers this one quite a lot. Not really. I did not describe the details of the antenna, the one we designed, right? So this is how it looks like. Internal, it has 4 layers, 3 substrate layers, 4 metal layers.
Sir, I think that slides are not visible to us.
Yeah. That's right. Let's wait a second. Okay, it's coming through. Okay, I will zoom it up. That's impossible. Try here. That is the box. That's not what I want to show you. This. Maybe I zoomed a little bit too much. Okay, that's better. Yeah, 3 layers of substrates, 4 layers of metal, some vias in between, and those are the metal parts. So this is an example of what is called the inverted F antenna. It's a bit more complicated than F because a typical, very simple inverted F antenna has a strip and one part like this, another part like this. That's why it's called inverted F. This one is a quite complex version of inverted F. with various metal sections, capacitive coupling between them. This is the original part we designed and implemented in FR4 using printed circuit PCB technology. But that part did not work very well because of the loading by the biocompatible material. So it resonated at the wrong frequency. Then we had to do this extension. We had to do a patch to get the resonance frequency correct. And after that, we got it to work. So that is an example of a PIFA, printed inverted F antenna, PIFA or PIFA. Then I mentioned in the slides, printed inverted F antenna, PIFA. Okay, the last few antennas I want to describe before we finish in some 15 minutes or so is more flexible wearable antennas. We have published a lot of papers. I can show you one and some slides. Let me find the PDF. This is again not the simplest one. It's a dual band, dual mode textile antenna on PDF. So it's now we are getting more complicated than the simple flexible embroidery type antennas. And this was published in IEEE Antennas and Wireless Propagation Letters. In fact, Roy published several papers with me when he was a PhD student and a postdoc. You can find all of them in IEEE Explore. Lot of details about the antenna configuration and how we tested them, radiation patterns, etc. The numbers and the gaps, etc. So I got some slides as well that is easier, I believe. So I will switch to the slides. This was presented, I presented this in International Microwave Symposium, the IEEE MTT Society flagship conference, some time ago. But this gives an idea about the flexible. Yeah, it's coming. So this covers two things. One is the flexible antenna. The other thing is an active antenna. Technically, because we have varactor diode in that. So, and we apply a bias to the varactor by changing the bias. We can reconfigure the operating frequency of the antenna, so we can tune it to a range of frequencies. The motivation is very similar to what I mentioned before: wearable devices, flexible antennas. Very similar to the previous presentation. But yeah, there are a lot of passive antennas, but there's there were not many, almost no active antennas that are wearable, flexible at that time. So our idea is to make them not just flexible, wearable, but electronically tunable. So this is some of the literature search at that time, others' work, not our work. And then we dipped into PDMS. Roy was very good in handling this. We developed a method to make these PDMS layers. And then we got commercial conductive fabric that you can buy as a conducting material. And you can cut them into various shapes. And the papers, our papers explain how you make them and the problems. We came across a lot of problems and which is better, which way is better. So we compared various fabrics, etc., and deformed them, squeezed them repeatedly to see which one is more stable, mechanically stable, detachments and um, to the fibers, conducting fibers. So at the end, we made the antenna, the passive antennas, and then make this active antenna. So it is again like a printed monopole type antenna. The interesting thing is we have a varactor diode and the bias. So by changing the bias, so you can see the couple of, this was a while ago, I believe these are the varactors, and then there's another chip inductor. So all integrated, they were covered by PDMS. So they are kind of sealed, water sealed. And that was very important because you don't want these antennas integrate to a jacket or something, right? And you want to wash the jacket. You want to put the jacket in the washing machine. So our testing was, the first testing was fairly easy. Put it in a body model and measured the performance. And we bent them to the shape of the head, etc., measured again. They were all good. But the third test was hilarious, very funny. We put the antenna into the washing machine and the delicate mode, and we washed it the complete cycle of 45 minutes. And then took the antenna out, dried it up a little bit, and connected to the network analyzer and measured it again. And it worked. It worked. So it can be machine washed. That's the toughest test for the machine of washability, right? So yeah, there's a lot of other details here, but you can find a lot of these things in the paper. Now, time to wind up. Let me see. I think we did cover pretty much everything. Let's share again the list I want to cover by today. Yeah, I think we are almost done. So we active integrated antennas, that's the one, the last one, the paper. Flexible wearable antennas, PFA we done. Yes, so that's pretty much all for today. If you have any questions, we have a couple of 5 minutes to answer. And as I said before, Next week, when I come back, I will go through the surfaces and what inspired us and the leaky wave antennas, some of the slides, and then so these things. And then maybe Thursday, the resonant cavity antennas, and then Friday, the metasteering, metasurfaces, and beam steering, phase correction, etc. So, any questions?
So, dear participants, if you are having any query, you can ask directly. Aarti
Yes,
Bansal,
go ahead.
you can ask.
Yes, Aarti, you can ask.
Aarti, you have joined as an viewer. However, we have created you as an contributor. I think you have changed your email ID somewhere, and that is why you are listed
Or
as.
if you want to type, you can.
You can also message somewhere here in the chat box. Aarti Bansal, you can type in the message box. Any other participant who is having some query? I think, sir.
Good morning. Good morning, sir. I'm
Yes,
audible. Ganesh.
yes, you are.
Uh, Sir, actually, we want to put the varactor diode in that flexible materials. How to solder it, sir, for that varactor diode and then biasing?
Oh yes, yeah. That's another challenge. You can't solve it, right? Because they're all flexibles, conducting this commercial flexible material. So we put. I think it connected with some sort of a conducting paste, but
Conducting.
everything was coated. After we done all that, we put another layer of PDMS on it. So it's all covered and kept together by PDMS. It's like a seal. The paper must
Above the
explain that. So,
PDMS, we need to solve.
yeah, so we avoided soldering by using conducting paste type connection.
Okay, sir. Thank you, sir.
Okay, then I think it's 8:30 night in my
Ashwani,
time.
I think one participant, Ashwani, raised his hand.
Okay. Yeah, go ahead.
Ashwani, are you there?
Sir, my voice is audible, sir.
Yeah, you are audible.
Sir, thanks for wonderful lecture. Sir, my question is that whether the PDMS substrate which are you talking about for the antenna fabrication, if actually I am just planning to integrate with the sensors, so whether it is possible it can be used in the practical real life or any other substrate is useful for the integration with the sensors.
Yeah, I think so.
Okay, okay,
I think you can integrate with sensors as well. We
okay.
haven't
Thank you.
done a lot of sensing, but we published a lot of papers on PDMS. After Roy Siam, Abu Siam did PhD, he used PDMS. So if you search my name and PDMS, you get quite a few papers.
Okay, thank you, sir.
Okay, then. So it's 8:30. I think I should have my dinner now.
Okay, okay.
um,
Sure, sir. Sir,
see you.
one question, number of the participants are asking one query that when we will be having that hands-on over the CST, as they are installed with the CST version.
Um,
Asking that if you will be letting us know, then we will be arranging the things.
it looks like all the slides and other things are taking a lot of time, and so I don't know we will have time. Is it we have to cut something to make room for that? It will not. It will not happen in the next lecture. Let's see how well we go,
Okay.
because the material slides and all that I have.
Okay, as you told me that that student should install the things, so they are done with that. So that is why I asked, and they are also asking.
So have they got that? Have they installed?
They have installed with the CST.
Yeah. So maybe if we have time, we will do it in the last couple of days.
Okay.
Maybe a little one.
Yeah.
That won't take much time, because I think the way we going, because that hands-on things take.
As per your comfortability, we can have that.
Yeah.
Okay.
Let's see how I have some ideas, and we can do it.
Okay, sir.
But the time is available time. We will try maybe one of them in the last couple of days.
Okay, sir. Thank you, sir. Thank you, sir, for your wonderful lecture, and I hope that you will enjoy your dinner.
You're welcome, and see you.
Okay.
See you Wednesday. Bye bye.
Okay. Bye bye.
Okay, sir. Thank you.
Thank you, all the participants. We will be joining tomorrow at 11 a.m. sharp. So I request all the participants that please join your session with the email ID you shared with us, as Aarti Bansal, Amrish, Ravi Kumar, Vinay Kumar, and Vishnu Kumar Mishra. They have joined, I think, with some different IDs. That is why they are available in viewer list. So I request that you should join with the email ID shared with us. Okay, thank you.
Okay, sir. Thank you.